Hi everyone, in this video we're going to look at pseudocode. So just a very small part of the methods course, but will turn up on your exam, likely exam 2. So it's important that you understand how to actually read it, and it is not overly difficult to read, but for majority of people it is fairly new. So it can be like learning another language, but we're actually not going into anything too complicated. Just keeping it simple. So if you can kind of understand what is happening in the pseudocode, then you're pretty much there. All right, we're not having to program anything. Pseudocode is basically just a fake code, so it's just, you know, looking at what is happening, maybe using plain language, basically. All right, all this theory here is just a bit of background on pseudocode. So you could have an algorithm, so basically the process of doing something, and pseudocode is just, I guess, putting that into some sort of coding language. All right, so what I'm just looking here at the understanding the problem. So you're thinking, what part of the screen is she referring to? All right, so we have inputs and then we got outputs. So basically we're going to put in some values and get something out. Hopefully you've watched now the bisection method video, and on that I do look at a pseudocode question. So our inputs were what the function was, the lower limit and the upper limit, and how many iterations we were going to do. All right, so we got an output from that problem. All right, what the midpoint was after the second iteration. So it's just a matter of understanding what it's asking. So if I'm just going to go past this flowchart start, and then some pseudocode notation. Not that you really need to know this language. I feel like you'd probably understand what is actually happening with the pseudocode, but it is there if you need it. All right. So with pseudocode, there's a whole range of topics we could apply it to. So piecewise functions, bisection method, which I went through in the other video, numerical evaluation of limits for derivatives, Newton's method for polynomials and other functions, polynomial approximations to transcendental functions. Oh my gosh, sounds very complicated. Counting in a probability context, simple simulations for probability, optimization of integer valued functions, simulations for sampling distributions, and numerical integration left and right interval values, trapezium method, point estimate. So it probably looks very complicated what we're doing here, and we can't do an example of everything. So I've got a whole range of examples we'll work through. It will be quite a long video. I strongly encourage you just to probably have a section in your bound book that has a few examples there. Then on the exam, you've got it to refer to. If it feels overly overwhelming, if it feels very overwhelming, then I would just say maybe just focus your attention on something else. Anyway, but give it a go. It is, I think, if you're a coder or you've done coding before, it's probably going to be a little bit easier to understand, but it's just a logic. All right, and we have to just follow that logic to, input something and to get some sort of output. All right, so I'm going to just have a look at some basic ones, and then we'll look at some more complicated ones. So here we have just a basic algorithm. And I'm just getting my pen ready for the video. All right, so what we've got, and this isn't from a past exam, so I think it would look a little bit more complicated than this. So basically, we're letting A equal 2. All right, and while A is less than 20, we're going to double A. All right, and then we keep going through that process. So basically, we start off with the number 2. All right, and while A is still less than 20, we're going to keep doubling it. So we're going to go 2, then we're going to double it to 4, and then we go through that process again. So we're going to basically be doubling it each time. So double 4, then double 16. And because we're still less than 20, which is what this while part is, so while A is less than 20, so 16 is less than 20, then we're going to double it. so 32. So we go through it again. 32 is now not less than 20. All right, so we're going to end. So we're going to print A. So our final answer is 32. All right, next one. An algorithm on the right will print the value. Okay, so this time we've got sum is starting with 2. For x is between 1 to 3 and y is between 1 to 2, we're going to keep adding on x and y, all right, until we get to the end. So we've got a limit here. So y is going from y to 2 and x is going from 1 to 3. Now with coding, we do start from the, so you can see here, we would logically go in this order here. But when we're looking at pseudocode, all right, we're going to kind of work a little bit backwards. All right, so we're going to do the y value and then the x value. So what I mean is, and I might do it going upwards like that. So we're going to start with 2, and then we're going to add on, because we've got y, I know it's written here x plus y, but the y appears first. All right, that's the next indent. So then we're going to add on y, which is 1, and then we're going to add on the first x value, which is 1. So we're going to, here's our sum, then we've got our y value and then our x value. All right, and we're going to add them together to get the next sum. So 2 plus 1 gives us 4. And then we start that process again. Now we do have to go through all the y values. So then we go y2, and then x1. So then we get 4 plus 2 plus 1 gives us 7. And then we go back to, because y only can be 1 or 2, so it goes back to 1. And then we go, sorry, I just had to pause. And then we go to 2, so the next x value. So 7 plus 1 plus 2 is 10. And then we go to the next y value, which is 2. And then 2. So you can see with my y's, I've got to go through them consecutively, and then for each x value. So we're going 1, 1, 2, 1, 1, 2, 2, 2. And then we're going to add them together. So it's going to be 14. And then we go back to 1, and then we're going to do 3. So 14 plus 1 plus 3 gives us 18. And then we're going to add 2, and then lastly, the last 3. So 18 plus 2 plus 3 gives us 23. And we've finished our numbers. So just to recap why we've done it in that order. So we've got to go back. So this is what we want to do. This is the sum. And we're doing the y values first. So we go y1 and then y2. So y1 with x1, y2 with x1, y1 with x2, y2 with x2. Right, so we're working through each y value and then the corresponding x values. So we end up with 23. All right, can we fit this on the page? I'm going to make it a bit smaller. All right, so for the algorithm shown opposite, the value of C when count equals 3. All right, so I think these questions were taken from Ed Rollo. All right, so we've got define f of x. All right, so here's f of x here. And, oh, this looks like yes, it's a bisection method question. So you can see how the coding for this one is different. Let me just go back to this one here. So this question here is a sample VCAR question. So see how it's a little bit more complex than this other one, which I think was taken from Ed Rollo. So still the bisection method, and you'd probably rely more on this one to be a VCAR question than this one here, but we're just going to go through it anyway. All right, so the main difference is in the VCAR one, it has defined what these things are. So it defined f of x, it defined a, b, and I think c as well. So you call it c or midpoint. Let me just check. Or mid. Oh no, I didn't do anything. Defined it down here. All right, so the max was the number of iterations. All right, so with our bisection method, so you saw on the previous question from the sample exam, it did say it was a bisection. This one doesn't. So what gives it away that is bisection is we've got two values and we're dividing it by 2. And we're actually then also multiplying f of a times f of c, all right, where c is your midpoint. The midpoint is likely to be c, but if it's something else like m, just expect f of m there. All right, so we've got our function. So remember, we can easily graph that to help us visually see. So to visualize what is actually happening. So if you want, you can graph it. Now, it would be quite time consuming to graph it, but maybe while you're still learning about pseudocode and the bisection method, you might want to sketch it. All right, so here it is, and a is between 2 and 3. Whoops. Oh, sorry. Let's do that again. All right, that's a bit better. That's the original graph, still my sine graph. So there you can see it is between 2 and 3, and we want to get closer and closer to this x-intercept. All right, so what we've got here is what we call a tolerance level. All right, so while b minus a is greater than 0.02, we're going to keep going through this pseudocode until we get a confidence level that is less than 0.002. All right, so with your bisection method, I do think it's, let me just have a look, I've got space. It's a good idea just to have your a and your b. All right, and then flow through like we did in the other video. So we went from, here we're going from 2 to 3, all right, so 2 to 3, and our midpoint is going to be 2.5. All right, so we're going to keep going until we've got a confidence level, and we'll see that on the calculator. All right, so visually I can see that 2.5, it's going to be between 2 and 2.5. So I don't even have to consider what this pseudocode is telling me, but let's do it anyway. So I know that the 2.5 is going to go on the B side and the 2 is going to stay on that side. But it's asking me to do this check, f of a times f of c. All right, so I'm just going to copy this. Hopefully, actually I'm going to just hold my computer over because it's going to probably not like me doing everything. All right, so let's just define it. All right, so there's our function. Let's do f of a. So a, remember, was 2 times c, so c being our midpoint, which was 2.5. I was like, what was it? All right, so if it is less than 0, we are going to apply, and I'm pointing to the screen, but you can't see me. We're going to apply the value, so it is negative. It doesn't matter what it is, we just want to know whether it's negative or positive. So it's less than 0. So that means we're going to apply that midpoint to B, which we've just done. Okay, so it does tell you in the pseudocode. If it was a positive value, then we apply the midpoint to A. All right, so we're going to keep going because the confidence level is currently 0.5. All right, so B minus A, 2.5 minus 2 is 0.5. All right, so halfway between 2 and 2.5, we can do without a calculator, so 2.25. All right, again, seeing it on my calculator, I can see it's definitely between 2 and 2.25. Now, I'm not going to even bother checking it because I want to save a bit of time. All right, so again, it's going to go onto the right side, so 2.5. So it's going to go between 2, I didn't write the right number, 2.25. All right, we still don't have that confidence interval, so we're going to keep going again. All right, so halfway between 2 and 2.25 is 2.125. Now, we might actually check it now because it's a little bit hard to see on my graph. I do think it's probably still less than 2.125, but let's just check it. All right, so our value of A is still 2, and we're going to multiply that by our midpoint, which is, sorry, f of our midpoint, 2.125. All right, and now it's positive. All right, so I was incorrect in thinking it was on the other side. So it is in fact on, needs to go to A. So now we're going from 2.125 to 2.25. All right, I'm going to find the midpoint between them because I still don't think we've got, we're meeting this tolerance. Let's just double check. So 2.25 minus 2.125. All right, and we get 0.125. So our tolerance level is too high. So let's keep going. Oh, I'm going to have to go up here. So let's just do halfway between 2.125 and 2.25. So you can see this is going to be too long to do on an exam, but let's just do it anyway. 2.25. All right, and then we're going to divide it by 2. Oops, not divide it by 22. Divide it by 2. All right, we get 2.1875. 2.1875. And we do need to check it because we can't see on the graph. Or actually, we could change our scale, but let's just check it. So we still do f of A. So in this case, A is 2.125 times f of C, 2.1875. And now it's negative, so that 2.1875 is going on the B side, so I might just throw an arrow. So it's between 2.125 and 2.1875. Again, let's check this tolerance. Actually, I know it's not going to be that high. So we're going to go again. All right, so the midpoint between those two, oh my God, I feel like we're going to be here forever, plus 2.1875 divided by 2. All right, 2.15625. All right, and then we've got to check. So f of 2.125 times f of 2.15625. And it's negative. So remember, when it's negative, it's going to be allocated to B. And 2.15625. I'm getting very small here. I'm really only going to have one answer, I think. Oh, actually, oh my God. All right, I didn't read the question properly. No wonder it was taking me forever. Oh gosh. Anyway, I was going to keep going until I no longer met that tolerance level, but obviously no, because that takes forever. All right, so find the value of C when the count is 3. Okay, sorry guys. Let's do what that actually is. Oh, I wish I could rewind now because that was very boring doing all that. All right, so first of all, count 0. So this is our first one. All right, we get 2.5. Oops. And then our second one. So we want the value of C. And then this is our third one. So the value of C to start off with was 2.5. Then after one iteration, it became 2.25. Then after 2 iterations, it became 2.125. And then after 3 iterations, it became 2.1875. All right, so that was your value of C. so that was still quite a few iterations to do. It did take us a while, but we did keep going, but we did have to stop at 3. So just a reminder to read the question properly. Okay, let's keep going. All right, question number 4. So here we've got some probability. So 3 dice are rolled at the same time. The algorithm shows shown opposite generates a sample space for this experiment. The print statement when count equals 4. All right, that's important to know. All right, so that's 4 iterations, gives 4x, the value of x is. So let's have a look at what we're actually doing. So we're going to start off with 0, and we're going to go from 1 to 6. And so for I from 1 to 6, for J from 1 to 6. So if you think about it being a dice, which it is, we've got 3 of them. So dice I, dice J, dice K, or die, I should say, 1 to 6. And what we're going to do for each iteration, we just add the number of the dice together, on the dice together. All right, so let's have a look at, so we're doing the first count. So count number 1. All right, so we've got count 1, and remember we work backwards. So we're going to do K first. So we're going to have K, then J, then I. All right, and we're going to do that until we get count 4. All right. So for count 1, we add I, J, and K. So for K, it's going to be 1, J is 1, and I is 1. So together, it's going to be 3. So we're going to have, for that one, it's going to print 1, 3. All right, so it's going to print the count number, which is 1, and then add up I, J, and K. And we're going to repeat that process. So for count 2, now remember, for K, we go up by 1, so it's going to be 2, 1, 1. So that's going to be 2, 4. All right, and then for count 3, K is going to be 3, J is going to be 1, and I is also going to be 1. So we get 3, 5. And you could probably see a pattern happening, so you could obviously do it a lot quicker. 4, 1, 1. So that one's going to be 4, 6. So the value of x is going to be 6. All right, so just remember we go from the furthest indent first. All right, so we go from K, J, I. So for K, we go through all 6 numbers, and J and I say is 1. So obviously there's going to be heaps of outcomes, and we're only doing it 4 times. So we can stop there. We don't need to keep going. All right, let's have a look at question 5. So for the code opposite, give the resulting printout. All right, so this is very short. So on a VCAR exam, it'll probably be a little bit more complex than this. All right, so for I from 1 to 4, print I cubed plus 2, and then we end. So we're going to substitute in 1, 2, 3, and 4 into I3 plus 2. So we've got different values of I. We've got 1, 2, 3, 4, and then we're going to just write what's printed out. All right, so substituting in 1 cubed plus 2 is 3. Then substituting in 2 cubed is 8 plus 2 is 10. 3 cubed is 27 plus 2 is 29. And then 4 cubed is 64 plus 2 is 66. All right, so that's what would be printed. 3, 10, 29, 66. Question B, for the code opposite, give the resulting printout. So for I from 1 to 5, so let's do that for I. 1, 2, 3, 4, 5. Now if I squared is less than 10, we're going to print I squared. Otherwise, we're going to print I squared plus 2. So let's do what I squared is first. So 1 squared is 1, 2 squared is 4, 3 squared is 9, 4 squared is 16, 5 squared is 25. All right, so remember if it's less than 10, we're going to print that. So we're going to print 1, 4, and 9. Now if it's not less than 10. So these two are not less than 10. We're just going to add 2 to them. So 18 and 27. All right, so we don't have any Newton's method, no bisection method. It's just pretty straightforward. And they're from Ed Rollo, a little bit simpler. I think these are from Ed Rollo, a little bit simpler than the VCAR exams. All right, so let's have a look at, I'll choose an easier question to start off with. This one we did on the bisection method video, so I'm not going to do that one again. All right. There's only one other question. Let's do this one. All right, so for question 5, and I think this is from the sample exam as well. All right, so for the algorithm below described in pseudocode, the algorithm below described in pseudocode estimates the value of a definite interval using the trapezium rule. All right, so this is a VCAR sample exam question. So notice how it's a little bit different to the previous ones we were doing. So it tells us what f of x, which is the function to integrate. We've got a, which is your lower terminal of integration, b, your upper terminal, and then n is your number of trapeziums. So we're just basically applying the trapezium rule using pseudocode. Now, all of this here is basically just telling you what h is. All right, so with your trapezium, your trapezium rule, your area of a trapezium. All right, so there's things we need to consider to do that rule, and that's all that's happening here. All right, so h is going to be defined as b minus a divided by n. The sum is f of a plus f of b. X is a plus h, and I is starting at 1. So I is usually your number of iterations. All right, so while I is less than n, what we're going to do is this, sum plus 2 times f of x. And we're going to let x plus h equal x, and then add 1 to I, so the next iteration. All right, so let's have a look at what function we're dealing with. Okay, so we've got a log function. Our lower limit is 1. Our upper limit is 3, and we've got 10 trapeziums. All right, so for this one, we only have to so we have to find the variable sum. So we're not finding the area. See how it's got area there? We're not finding the area. We're just finding the variable sum after 1 iteration of the while loop. So basically, we don't need to do too much here. It's just an understanding of a small component of the pseudocode. All right, so let's just work out what everything is. So for the sum, all right, here it is. The sum is equal to sum plus 2 times f of x. All right, so we've got to actually substitute everything in. All right, so this is, we want to know what this is. I know I've got sum written twice, but sum has been, you apply one sum to a new sum. Okay, so the sum, which is here, is f of a plus f of b. All right, so there's the sum part, plus 2 times f of x. So f of x was log ex, and x is not x, but it's a plus h. All right, now the thing is, h hasn't been defined. All we've got to find is this value here, which is a, this value here, which is b, and this is n, our number of trapeziums, right? Because it defined it up the top. Where did it define it? Here. Right, A, B, N. Not Australian Broadband Network. All right, so let's just do a little bit more work here. So f of a, so a, let me just scroll down, is 1. B is 3 times, plus 2 times log base E. A, remember, is 1. And H is defined as this. Let me just get rid of this so we can see it a bit easier. B minus A, so 1 plus B, which is 3, minus A, which was 1, divided by H. And not H, where am I? Divided by N. So N is 10. So I'm not reading it. So this is what I was reading here. B minus A divided by N. So now we can put all that into our calculator, which is very, very time consuming. All right, so it's just a log function. All right, so f of x is log, so I'm just going to do f of 1 plus f of 3. Whoops, sorry, log of 3, I didn't define it. 3 plus 2 times natural log of 1 plus 3 minus 1 is 2. So 2 divided by 10. All right, and then we get 1.46 blah, blah, blah. All right, so that's what our sum is. So answer is C. So a little bit time consuming. I don't think it would take you that long in an exam. But just substituting everything in. All right, we only had to do the sum. All right, so the sum times 2 times f of x. We go back. Let me just highlight this. Oops. Different color. All right, so we needed to find the sum. So here's the sum, which is calculated by f of A minus f of B. That's what we did here. All right, A and B were defined. Yep, 1 and 3. And then we had to do 2 times f of x. Now f of x was log ex, but x is defined as a plus h. And then the annoying thing is that h is also defined as b minus a divided by n. Now you could do all this straight into your calculator, maybe to save a little bit of time, but it seems probably more complicated than it is, but it's definitely time consuming. It's a little bit frustrating. All right. Now I'm just conscious of how long this video is, so I might do this question here. So question 14. So this is from the NHT exam. All right, so the NHT exam. These questions, so this first question I did in the Newton's method video. Sorry. Oh, and there's another one there. All right, maybe we'll do this Newton method one first, and then we'll do that last one. All right, the following algorithm applies Newton's method using a for loop with 3 iterations. All right, so let's highlight that's important, because remember I didn't realize that before. So in those Ed Rollo questions, they called them counts. Here we're calling them iterations. Probably in VCAR they're going to call them iterations, so just be aware of that. All right, so we've got f of x, we've got d of f of x, which is the derivative, and x0, which is your initial value. All right, so we've got, here it's been defined. So here is your f of x. All right, so there's f of x. And they've actually also given you the derivative, which is pretty cool. And then here's your initial estimate. All right, so we're going to do Newton's method for 3 iterations. All right, so if you can interpret that from this, all right, so that's all Newton's method is. It's told us what the function is. It's told us what the derivative is, even though we could work that out ourselves. And it's told us the initial value. So remember on the calculator, we can just do that straight away. So we're going to define it. So define f of x is equal to x cubed plus 3x minus 3. All right, we don't have to define the derivative, because remember, if we just scroll up to where we're doing All right, doesn't matter which one we use. All right, so I'm just going to copy that down. All right, and we've got an initial value of 1. So it's asking us to do the return value of the function is closest to. So we want to do it 3 times. All right, that's what it's basically doing. We're doing it for 3 times, and what is the value we're returning? All right, so I just did it once. I'm going to highlight that, drag that down, and then we're going to do answer. That's twice, and there's 3 times. So 0.81773. So a lot quicker than that previous one we just did. So that was on last year's VCAR exam. All right, now let's have a look at this one here, question 14. All right, so parts of the graph of 2 functions, f of x equals x and g of x equals cos x, are shown below, where x is measured in radians. The pseudocode below describes a simple algorithm to find the point where the 2 functions intersect. So to find this point here. All right, so which of the following will the function intersect 0.6, 0.8 return? So we're basically, what we're doing is we've got 0.6 and 0.8, and we can see it is between. Now this is not the bisection method, all right, it's just looking at finding the intersection between 2 graphs. All right, so while x is less than x1, so this is our x0 and this is x1, so it is less, so we're going to just do this little test. Cos x minus x. Is it between negative 0.01 and 0.01? All right, so let's just check that. All right, so x to start off with is x0, so 0.6. So cos of 0.6 minus 0.6. All right, and we get 0.225, blah, blah, blah. And it's definitely not between our intervals. So basically we've got our inequality signs here. All right, it has to be between negative 0.01 and 0.01. So if it was between them, then we can return x. So we would return 0.6, but it's not. So we're going to have to add on 0.01. All right, so then we get 0.6 plus 0.01. So our next value is 0.61. And we do that process again. All right, let me just get the calculator. All right, and we can just put it straight in here. 61, 61, and then it's not in between. So let's add another 0.1 until we're between those 2 intersections. All right, still not there. So we're going to add another 0.1. Oops. All right, still not. Oops, why am I doing that? So to keep going, I'm looking at the answers. We've got 0.73 and 0.74. So I could keep going, but I'm just going to just go to straight 0.73. It's probably easier instead of keep doing it. All right, so we've got 0.15. So we're still not within that interval. So I'm going to go to 0.74. All right, and then we get negative 0.001. All right, so if we just have a look at the decimal places, this is 0.01 or negative 0.01. So this is clearly less than that. Not less than that, it is closer to 0 than that. So it's more than that, so it's closer to 0. All right, so it's going, your answer is going to be 0.74. All All right, so let's finish with this question, which is I think the last one in your little booklet. Sorry we haven't gone in order, just jumped around all over the place, but hopefully you'll find this one. So it's another one on Newton's method. So let's read through it. So consider the algorithm below, which uses Newton's method to estimate the solution to an equation of the form f of x equals 0 with a tolerance of 10 to the power of -4. So we know it's Newton's method, which is great because we don't actually really need to understand the pseudocode to do Newton's method, but we do have to just work out what it's asking for. So we can't just assume that it's going to ask for the output. It might ask for something else. So let's just have a look. So this question is asking for the output after the second iteration of the while loop would be closest to. So let's have a look at what's going on here. We've defined Newton's method. So remember, you've got a function and an initial value. So here it is here, 5 minus x cubed, and your initial value is 1. So while I is less than 100, so we're doing 100 iterations. Obviously, we're only doing one because that's what the question says. We're going to apply basically Newton's method. All right, so there's your x. There's your minus f of x divided by the derivative of f of x, which is Newton's method. It's just written in a really weird way. And it doesn't help that all these squiggly lines are on there. All right, now this part here, you're probably thinking, well, this is a bit new. That's just a tolerance level. All right, so remember when we applied Newton's method, it gets closer and closer to the actual value. So that's all that means. And it doesn't actually apply with this question because we're only doing one iteration. All right, so what we're going to do is just apply this. All right, so if it's between, all right, so if x next minus x current is between those tolerance level, then we're going to return so we just want basically just one oh my god, I can't think, one iteration. All right, so we're going to return this f current. All right, just one iteration. I don't want to complicate things. Okay, so let's define, just like we did before. So define f of x is equal to 5 minus x cubed. All right, so we've defined it. And remember, we can just drag this down again. So we're going to copy it and paste it. So our first value, remember, is 1. It's defined here. So x equals 1. And there it is. That's just one iteration. All right, so 2.333. Sorry, let me read the question properly. So we need to do it again, the second iteration. Oh my gosh, you can tell I'm very tired. All right, so we're going to do that one more time because that was just only one iteration and I didn't read the question properly. So let's do the second iteration. We could put the answer in, but we're going to put that in. All right, there it is, 1.86, blah, blah, blah. All right, so your answer is D. Now, let's just go back up and see what this tolerance level is. All right, not that it should actually make much difference, but it's, you know, when you've got a tolerance level, so it's just the difference between your two answers. All right, so if this is between, all right, let me just drag that down. All right, so we've got 0.474, so there's a big difference between the two. All right, it's asking for quite a small tolerance level. So if I just do negative 10 to the power, whoops, sorry. Oh, let's just do 10 to the power of negative 4. All right, it's a very small tolerance. So it's going to be negative 0.0001 to 0.0001. So if I kept doing my, sorry, let me just copy and paste it down. If I kept doing my iterations, all right, and then I'm just going to put answer in. Whoops, there. Move that one down. All right, and then answer. All right, so basically I got to keep doing that, and you can see you get closer and closer. So when that tolerance level, and it might have reached it here, let's just have a quick look. So I'm going to highlight that and then take away this. So you're just looking at the difference between two consecutive values. Oh yeah, definitely. I probably reached it up here. All right, so maybe even, I don't know. Anyway, so that's what the tolerance is. So just the difference between two numbers, because we know that when we keep pressing enter, the values get closer and closer together. All right, they're very, very similar. All right, let's leave it there, 45 minutes. I'm sorry it's not the most exciting video. I do find it very, very challenging to teach, but hopefully on your exam, we get a straightforward pseudocode question. All right, bye guys.